I am Sara Tamy, independent researcher from Morocco. My presentation anticipates potential applications of nanotechnology in Industry 4.0 towards enhancing products and processes. So this is my presentation roadmap. First of all, I will give a general introduction in which I will produce or provide the context and framing of my talk. Then I switch to technical exploration, case study, AI-driven nanosensors in Industry 4.0, challenges, risk mitigation and regulation. And before conclusion, I will give some perspective and transformative impact. So the shift to intelligence manufacturing demand material and systems that are I have to. That are responsive, adaptive, and efficient. Nanotechnology and Industry 4.0 share a common goal, enhanced precision, integration, and performance. So Industry 4.0 represents top-down intelligence, where data-driven automation and real-time analytics guide industrial processes. Nanotechnology, on the other hand, introduces a bottom-up intelligence, embedding sensing and adaptive capabilities directly into material at nanoscale. So this convergence is not additive, but it's synergistic, forming the basis of a new industrial paradigm in which intelligence is embedded from the atomic scale to the operational and strategic levels. Here I will briefly give presentation of transformation from Industry 1.0 to Industry 4.0. So the three industrial revolutions of the past were all launched by numerous technical innovation. The first one is known by the mechanization in the end of 18th century. The second industrial revolution, also known as the technological industrial revolutions. Here we have the use of electricity, which allow mass production. The third one is related or is marked by the rise of computer technology and automation, including the use of PLC and SCADA systems. Since 2011, we have the first industrial revolution, also called Industry 4.0 or Smart Factory. It's allow the transformation of industrial manufacturing systems through the using of new technologies or enhanced technologies such as industrial IoT, smart gateway, and other. The presentation of the concept was at the Hanover Fair. It was a strategic project of the German government to support the digital revolution and promote the computerization of manufacturing. So Industry 4.0 allowed to create the link between the physical, digital, and biological spheres and guarantee the interconnection, which led to enormous economic impacts. To achieve this, it relies on several key technologies such as cloud and fog computing, mobile technologies, machine-to-machine communication, 3D printing, robotic, big data analytics, Internet of Things, RFID technology, and of course, cybersecurity, because we have to protect data and communication in this context. The core of Industry 4.0 is related to interoperability, decentralization, virtualization, real-time capability, modularity, and service orientation. It's transforming almost every industry in every country, and scope of these changes is leading to the transformation of entire systems of production, management, and governance. So here we have the strategic objectives of Industry 4.0. Agile production, zero defects manufacturing, decentralized decision-making, and energy resource optimization. Together, they provide a roadmap for more efficient, intelligent, and sustainable industrial processes. Now we shift our focus to another view of nanotechnology, highlighting its fundamental principle and applications. There are differences between nanoscience and nanotechnology, of course. Nanoscience is presents the convergence of physics, materials, science, and biology dedicated to the exploration and manipulation of matter at the atomic and molecular dimensions. Nanotechnology applies the principles of nanoscience to enable the precise observation, control, and fabrication of functional structures and systems at nanoscale, typically between 1 and 100 nanometers, to create advanced materials, devices, and systems with novel functionalities. Let's take a brief look at the history of nanotechnology. The first ever concept was introduced in 1959 by Dr. Richard Feynman during his famous lecture, "There is plenty of room at the bottom" at Caltech. In 1974, Japanese researcher Norio Taniguchi formally introduced the term nanotechnology, defining it as the manipulation of material through the processing of individual atoms and molecules. Early 2000s, we have the first commercial application of nanotechnology. So nanotechnology is driving revolutionary progress in IT, medicine and healthcare, energy and sustainability, transportation, food safety, environmental science, and homeland security. So having explored Industry 4.0 and nanotechnology, and we now turn to their intersection and the synergy they create. First, advanced material enables stronger, lighter, and more durable components, enhancing the performance of industrial systems. Next, we have nanosensors integrated with IoT, allow ultra-sensitive real-time monitoring of processes, providing highly accurate data for decision-making. These technologies also contribute to energy efficiency, improving storage, and reducing overall energy consumption. Precision manufacturing at the nanoscale allow unprecedented control over processes, ensuring higher quality and consistency. Enhanced connectivity improves the communication between machines, creating a more responsive and integrated production environment. And of course, the integration with AI allows self-adjustment systems. These capabilities drive smarter, more flexible, and sustainable industries. The initial phase of Industry 4.0 focuses on digitalization, automation, and interconnectivity. The next step is defined by the materials and systems that are not just connected but intelligent and reactive at nanoscale. So nanotechnology enables this shift by unlocking nano-functional materials capable of real-time sensing, self-adjustment, and interconnection with cyber-physical systems. Nano-enhanced manufacturing processes that adapt at molecular precision. Embedded intelligence throughout nanosensors feeding higher resolution data into AI system. So this section focuses on how nanoscale optimization is transforming industrial processes. First, the integration of nanostructure catalysts and material enables higher reaction selectivity, reduced energy consumption, and minimized variability. Intelligent manufacturing systems, embedding nanosensors and nanoactuators within production lines, facilitates real-time, self-adaptive process control, improving precision and yield. Nanometrology and quality assurance, advanced nanoscale characterization tools provide unprecedented accuracy in process monitoring and defect detections. Sustainable manufacturing, nanotechnology-driven enhancements in energy conversion and material efficiency contribute to greener and more circular production models. So nanotechnology converges diverse scientific fields to redefine industrial production. Physics enables nanoscale imaging and manipulation of atom structure for precise material control. Chemistry designs functional nanomaterials such as carbon dot nanostructures for catalysts and sensors. Biology provides insights from biomolecular and cellular nanoscale studies, inspiring biointegrated manufacturing and biosensors. So IT promotes smart manufacturing with embedded nanosensors and implementation of new approaches for data-driven adaptive process control. Nanotechnology is redefining end products in the nano-industrial paradigm throughout 4 key areas. First, we have advanced functional materials. We have also smart and responsive products, miniaturization and system integration, surface and interface engineering. As a practical illustration of nanotechnology in action, consider the role of AI-driven nanosensors in Industry 4.0. So why nanosensors outperform traditional sensors? It allows to enhance sensitivity, detects extremely low concentration of chemicals, biomolecules, or physical changes, enable faster and more accurate diagnosis with highly personalized treatments. Also, it allows to improve specificity. Functionalized nanomaterials are engineered to selectively recognize targets, molecules, or environmental conditions. Data also collected from multiple nanosensors are integrated and analyzed using advanced AI, machine or deep learning algorithms, which enable to improve the efficiency and reduce error, both false, positive and negatives. We have another benefits. It's real-time monitoring. High-resolution data acquired by nanosensors is continuously collected from machines and production lines. Advanced analytics detects early signs of equipment degradation, enabling predictive maintenance strategies that prevent unplanned downtime and reduce maintenance costs. Also, real-time feedback loops facilitate dynamic adjustment to process parameters, improving product consistency, operational safety, and overall process reliability. Miniaturization and integration is another advantage of nanosensors. So the nanotechnology enables the development of sensors that are much smaller and more energy efficient than conventional ones. NIMS presents a revolutionary fusion of nanotechnology and mechanical engineering operating at nanometer scale. They exploit physical phenomena such as quantum effects and surface forces, offering unprecedented performance and functionality that is unattainable with MEMS devices. When combined with two-dimensional materials like graphene, they enable the fabrication of ultra-thin, flexible, and highly integrable sensors, paving the way for smart, high-performance systems ideally suited to Industry 4.0. Also, self-powered nanosensors harvest ambient energy from vibration, motion, heat, or light by using a lot of technologies or fundamental, such as piezoelectric, pyroelectric, triboelectric, and other. So all that allow to get a lot of benefits. For example, continuous and maintenance-free operation, reduce battery waste, enhanced reliability and scalability, and support sustainable and autonomous industrial IoT networks. So every technological revolution has its bright and dark sides. So while nanotechnology and Industry 4.0 unlock incredible possibilities, open a new horizon for innovation, they also bring challenges that cannot be ignored. The first challenges we have technological challenges. The integration of sensor across manufacturers is complex. We have issues such as interoperability, wireless communication, energy harvesting, and simple preparation. Second, cybersecurity and data integrity become critical in highly connected smart factories. And third, scalability and real-time processing of high-volume sensor data remain a significant challenge as factories generate enormous amounts of data. Beyond the technological challenges, we have also cost and knowledge barriers. Another critical aspect is standardization and regulatory challenges. First, there are a pressing need for unified protocol and reference architectures to ensure interoperability across systems. Second, compliance with safety, environmental, and ethical regulation must be maintained. Third, overcoming organizational resistance to automation and perceived technological risks. So to address these issues, companies are increasingly turning to risk mitigation strategies. This include predictive maintenance, scenario simulation, and proactive monitoring. In addition, the adoption of zero trust architecture and the use of machine and deep learning model, which allow to get to secure and resilient operations. The adoption, of course, we need to adopt standardized protocols such as OPC over TNS and 5G URLLC to ensure reliable communication between nanosensors and existing systems. Coordination of digital models to enable large-scale deployment and predictive maintenance. Nanosensors employ green manufacturing practice and sustainable technology to reduce waste, optimize energy utilization, deliver high-performance solution with reduced ecological footprint. So by using simulation and digital twins, nanosensors deliver precise real-time data to enhance simulation, forecasting, and system optimization while reducing costs and mitigating risk. The integration of advanced digital technologies such as blockchain, cloud, big data, and AI allows to improve industrial performance, security, and traceability. But we have also new challenge which will be the management of data generated of this network. And finally, digital sovereignty and end-to-end trust ensures control, integrity, and confidentiality of industrial data with proactive protection using zero trust model and AI approaches, allowed to guarantee transparency and resilience across the entire industrial ecosystem. So to summarize my talk, nanotechnologies are fundamental catalysts for Industry 4.0. They transform both process logic and material behavior. Their convergence with AI and industrial IoT paves the way for truly intelligent production ecosystems. This synergy allows you to improve productivity, streamline maintenance, and reduce costs. And they promote the emergence of autonomous, safe, and sustainable production ecosystem. However, it's essential to balance preventive measures with promoting innovation, which require the close collaboration across multidisciplinary fields, including physics, biology, chemistry, and engineering. This multidisciplinary collaboration drives the transformative power of nanotechnology across Industry 4.0. Here some are the references I used to prepare this presentation. I have included here my contact details, so you can reach me via email if you use the first query code or access directly to my ResearchGate profile by using the second. So thank you very much for your attention.